Hi, welcome to Altair Engineering, SAE Baha. Today in this video, the topics which I am going to cover are as follows. What is FEM? How the results are interpolated from a few calculation points. What is degree of freedom? When to use 1D element? Types of 1D element? When to use 2D element? Different types available in hypermesh for 2D elements. How not to mesh, the industrial rules for not to mesh, then quality checks for 2D element, when to use 3D element, then we will discuss different types of 3D element. There are some degrees of freedom for solid elements, then quality checks for Tetra element, and there are some important quality checks also for brick elements. So we will discuss all these topics in this video. So we will start with what is FEM. FEM stands for finite element method. Finite element method is a numerical method. It is a mathematical representation of actual problem, and it is an approximate method. It is also termed as FEA. Both are the same terms. So FEA stands for finite element analysis and FEM stands for finite element method. Both are same. So we will start with the definition of FEA. So FEA stands for finite. The finite element method only makes calculation at limited finite number of points and then interpolate the results for entire domain, surface or volume. So in FEA, in FEM we can define the FEM as, we'll divide these three terms and define them individually. So first we will define what is finite. Any continuous object has infinite degrees of freedom and it is not possible to solve the problem in this format. The finite element method reduces the degrees of freedom from infinite to finite with the help of discretization or meshing, or we can say the discretization or division of the entire domain is also known as meshing. Meshing contains nodes and elements. Then we define elements. All the calculations are made at limited number of points known as nodes. The entity joining nodes and forming a specific shape such as quadrilateral or triangular is known as elements. To get the value of variables, say displacement, anywhere in between the calculation point and interpolation function as per the shape of the element is used. So in this way elements can be defined, and the last is method. Then there are three different methods to solve any engineering problem. Finite element analysis or finite element method belongs to numerical category. So what is FEM stands for, I will explain that. If we consider this circular object, so it will have infinite degrees of point on which we can find the calculations. For say, for example, let's suppose we want to find the displacement. So we can find the displacement values for all these points. So there are total number of infinite number of points for a singular circular object. So if we consider 6 degrees of freedom per point, so there are total number of equations generated is infinite. So it is next to impossible to calculate these many number of equations. So what we do in FEM, we divide the circular object or the complete domain into some distinct interpolation points. That is, we create some nodes, and on these nodes the software will generate the equation and solve it for the results. Say for displacement, it finds the values of displacement at these points, and with the help of interpolation function it calculates the value in between any object. So if I want to define what is meshing, so if I'll take one more example. If I apply force in this location and will fix this side, so to find the resultant displacement, we want to find the displacement for each and every point. So to find the displacement for each and every point, it's very difficult, or it's next to impossible. So in FEM we create an elements with the help of nodes, or we discretize this object into different set of elements and nodes, and by using those elements and nodes, software will using the interpolation function, software calculates the value of displacement for the entire domain. So meshing is required to find out the value of any results for the entire domain. Meshing is required to discretize the object to a limited number of points. So in this way it works. Then we move towards the next topic, that is how the results are interpolated from a few calculation points. So it is okay that FEA is making all the calculations at limited number of points, but the question is how it calculates the value of the unknown somewhere in between the calculation points. This is achieved by interpolation. Consider a 4-noded quadrilateral element as shown in the figure below. As you can see here, a chord 4 element uses the following linear interpolation function. So for each element we have defined an interpolation function, and software uses that interpolation function for different types of shapes of the elements. So by creating nodes and by joining these nodes, software creates it will generate an element. So for each element we have an interpolation function. So for chord we have the interpolation function as this. If we consider, we can create a tria element. So for tria element we have a different interpolation function. Similarly for tetra brick, that is the 3D elements, we have different interpolation functions. So there are different interpolation functions available in HyperWorks suite to find the results in between the calculation points. So calculation points are the nodes on which the software calculates the result, and by using these interpolation functions find out the result in between the entire domain. So FEA calculates the value at outer nodes, that is 1, 2, 3, 4, that is A0, A1, A2 and A3 are known. The value of variable anywhere in between could easily be determined by using specifying x and y coordinate in above equation. So by just specifying the x and y in the above equation, we can easily find out the value of, say for example, displacement or stress for the entire domain. Now we will look for an 8-noded quadrilateral element. For 8-noded quadrilateral element, the following parabolic interpolation function is used, that is u is equals to a0 plus a1x plus a2y plus a3xy plus a4x square plus a5y square plus a6x square y plus a7xy square. So for a 8-noded, that is a second order chord element, the formula used for the interpolation function is this. So the software calculates the result for all these 1, 2, 3, 4, 5, 6, 7, 8 nodes, and then to find the result in between this element or this area or this domain, the software use this interpolation function, and by just specifying the coordinates of x and y, we can find the results in between the entire domain. Then we will move towards the next topic, that is what is degrees of freedom, that is what is DOF stands for. In the example above, an object is fixed at one end and a force is applied at point P. As you can see here, the object is fixed from here and force is applied at this point. So due to the force, the object deforms and point P gets shifted to new position P dash. When can we say that we know the solution of above problem? If the answer for this question is if and only if we are able to define the deformed position of each and every particle completely. So we can define this deformation only and only if we can define the position of each and every particle of the deformed shape completely. So the minimum, now we can define what is degree of freedom. The minimum number of parameters that is motion, coordinates, temperature, etc. required to define the position of any entity completely in space is known as degree of freedom. So degree of freedom means the minimum parameters required to define any entity, that is defined to define this point completely in space. The minimum parameters required are known as degrees of freedom. Now we'll consider an example. Consider a following example of 2D planar problem. Suppose the origin is at bottom left corner and is known. So if we know the origin, then to define the position of point A completely with respect to origin, we need two parameters, that is x1 and y1. In other words, or in the terms of FEM or FEA, we can say that 2 degrees of freedom, that is translation along x-axis and translation along y-axis. So to define point A completely in space, we require 2 degrees of freedom, that is translation along x-axis and translation along y-axis. Now consider that the point A is a part of line. Now to define a line completely in space, we require one more angle to in addition with the 2 translation, that is 3 degrees of freedom, that is 2 translation along x and y, and 1 rotation, that is the angle or the axis around which it is rotated. Now let us suppose that point A and B are shifted out of plane and the line is rotated arbitrarily with respect to all the 3 axes. Then the minimum number of parameters to define the position of point A completely would be 6 degrees of freedom, that is translation along x, y and z axis, that is ux, uy and uz, and rotation about x, y, z axis, that is theta x, theta y and theta z. So we define 6 degrees of freedom to define point A and B, which is being shifted out of the plane, and then the line joining point A and B are rotated arbitrarily with respect to all the 3 axes. So at the end we can define that degrees of freedom is very important concept. So at the end we can define degree of freedom is very important concept. In FEA we use it for individual calculation points. The total degrees of freedom for a given mesh model is equal to number of nodes multiplied by the number of degrees of freedom per node. Now we'll move towards the next topic, that is when to use 1D element. When one of the dimension is very large in comparison to other two, that is if we look on this example, the length of this beam is 1000 mm and the cross section of the beam is 10 mm and 5 mm. So one of the dimension is very large as compared to other 2 dimensions. In that case we use 1D elements for FEA analysis. The different options or the different parameters required for 1D elements are: the element's shape used for 1D element is line. The additional data from the user, that is the additional input required to simulate 1D element in FEA solvers, are the remaining 2 dimensions, that is cross-sectional area. There are different types of 1D elements available in hypermesh, such as rod, bar, beam, pipe, axisymmetric cells, etc. The practical applications for the 1D element simulation are long shafts, beam, pin joints, connection elements, etc. Then we move towards the next topic, that is the types of 1D element. There are different types of 1D element available in hypermesh. So they are as follows. We'll start with one by one. So we'll start with rod. Rod supports only tension and compression and torque for some softwares. So in rod element, it supports only translation along X particular. So rod supports only axial loads, that is tension or compression about particular axis, or rotation about that particular axis, that is the twisting moment. So practical application of rod or the points where the rod element can be used are tension compression members like truss, shaft subjected to torque, and connections of elements. So to connect the different elements for the gap simulation or something like that, we use rod element. Then we'll discuss with the next type of 1D element, which is bar. Bar supports all the 6 degrees of freedom, that is it supports for translation along x, y and z axis and rotation about x, y and z axis. But bars are only applicable for symmetric cross section. So the practical application of bars are, these are the shafts subjected to multi-axial loading. Where the shafts are subjected to multi-axial loading, we can use bar elements. Where the bolted welded joints are, we want to simulate, we can use bar elements. Also we can use bar elements for the connection of the elements. Then we move towards the next topic, that is the next point for 1D element. The next type of 1D element is beam. Beam is same as bar, but it also supports unsymmetric cross sections, that is shear centers and warpage. So beam also supports all the 6 degrees of freedom, but it also supports the unsymmetric cross sectional areas. The practical application is also same as bar, but addition to it, it also have a unsymmetric cross section application also. For the practical application where the unsymmetric cross section is used, we can use beam elements to simulate in FEM solvers. Then we discussed with next type of 1D element as pipe. Pipe is also same as beam element, except that it has an internal non-zero diameter, so they are hollow. If we consider a hollow pipes, so we can use pipe elements. The practical application where the pipe elements are used are piping systems, structural analysis. Then we have one more type of 1D element, that is axisymmetrical shells. Axisymmetrical shells only support translation along x axis, translation along z axis and rotation about y axis, that is degrees of freedom 1, 3 and 5. That is the z axis for the symmetry and x axis as a radial axis. These are used for the object symmetric about the axis of rotation and subjected to axisymmetrical boundary conditions. The practical application where the axisymmetric shell elements are used for FEM solver are thin shell pressure vessels, cylindrical conical objects. So these are the basic introduction for. Now we will move toward the next topic, that is when to use 2D elements. So 2D elements are used when two of the dimensions are very large as compared to the third dimension. So if we consider this sheet metal component, so the two dimensions are very large as compared to the third dimension, which is the thickness of the sheet metal component. So in this case we use 2D elements. Generally for any FEM solver, we create a mid surface for 2D shell elements and then assign the thickness to it to simulate the practical problem in FEM. Now we will discuss the different criteria for 2D element, that is the element shape. So the element shapes available for 2D element are quad and tria. Quad stands for quad elements and tria stands for triangular elements. We have two types of tria elements in hypermesh, that is equilateral trias and right angular trias element. Additional data from the user required to simulate any 2D element is remaining dimension, that is thickness. We have to input the thickness to simulate any 2D component. Then the element types available for 2D element is thin shell, plate, membrane, plane stress, plane strain, axisymmetrical solids, etc. The practical application for sheet metal parts are for sheet metal parts we use 2D elements. For plastic components like instrument panels we can use 2D elements. Then we move towards the types of 2D elements available in HyperWorks. So we have two types of 2D elements. First is tria, second is quad. In tria we also have two different types of tria element, that is linear tria element, which is having the interpolation functions or the nodes on the line intersection, and a parabolic tria which has a nodal points at all in the midpoint also. So this is a 6-noded tria element. Similar the case for quad element. We have a linear 4-noded quad element. Also we can simulate the same problem using 8-noded quad element. Then we will move towards the next topic, that is how not to mesh. There are certain industry standards where the meshing are not acceptable. So we'll discuss that. So first it is that back-to-back triangles should be avoided. That is two tria elements should not be connected to each other directly. This is because the tria elements have more stiffer. They are more stiffer as compared to quad. So if tria elements are connected back to back or they are very close to each other, so the stiffness of the component on that particular region increases, and it may change the result of stress and displacement on that particular zone. Then the second point is, on planar surface triangular elements should be avoided. So if possible we can avoid the triangular elements. We should avoid the triangular elements because the reason is same. The triangular element have a higher stiffness as compared to quad. So in planar we try to remove the triangular elements. Now the third is no mesh transition on constant radius fillets or curvatures. The mesh transition should be carried out on planar surfaces because maximum failure location is found out at the fillet regions or curved regions. So we should not have any mesh transition on that region because the interpolation function may change due to the mesh transition. So we should go for the smoother mesh on the fillet transitions to simulate the results more appropriately. Then the fourth point on that is circular holes should be modeled carefully with washer. The range for the washer is from 1.5 to 2 times the diameter, and a minimum of 2 layers around the hole should be created by 2D mesh to simulate the results more appropriately. Then the fifth point is, instead of zigzag distribution, a structured or smooth mesh is recommended. So it always better to have a smooth mesh pattern instead of a zigzag pattern. Then we should follow the feature lines, that is nodes should exactly lie on the edges so that we can simulate the proper geometry by discretizing that geometry using our elements and nodes. So all the nodes should lie on the geometrical features to simulate it properly. Then there are different quality checks for 2D element. We will discuss each of them one by one. So first is warpage. This is the amount by which an element, or in the case of solid element and element phase, deviates from being planar. Since 3 point defines a plane, this check is only applicable for quad elements. The quad is divided into 2 trias along its diagonal, and the angle between the trias normal is measured. Warpage of up to 5 degrees is generally acceptable. So the warpage value should be less than 10. Ideal value is 0. So for industrial standards, the warpage should be less than 10 degrees for a quad element. Then we will discuss aspect ratio. There is also one quality check for aspect ratio. This is the ratio of the longest edge of the element to either its shortest edge or the shortest distance from the corner node to the opposing edge. For the 3D element, each face of the element is treated as 2D element and its aspect ratio determined. The largest aspect ratio among these faces is returned as the 3D element's aspect ratio. Aspect ratio should rarely exceed 5:1. Ideal value for aspect ratio is 1. Acceptable should be less than 5. Then we move towards the next quality check, that is skew. Skew for the triangular element is calculated by finding the minimum angle between the vector from each node to the opposing midside and the vector between the two adjacent midsides at the each node of the element. The minimum angle found is subtracted from 90 degree and reported as element skew. Then we move towards the chordal deviation, that is the next check for 2D elements. Chordal deviation can be defined as the curved surfaces can be approximated by using many short lines instead of true curve. So chordal deviation is the perpendicular distance between the actual curve and approximating line segments. Then we move towards the next quality check for 2D element, that is length minimum. So the minimum length, element length are calculated using one of the two methods, that is the shortest edge of the element. This method is used for non-tetrahedral 3D element. The shortest distance from the corner node to its opposing edge or face in the case of tetra element referred as minimal normalized height. Then we move towards the next, that is Jacobian. This measures the deviation of element from its ideal or perfect shape, such as triangles deviation from equilateral. The Jacobian value ranges from 0 to 1, where 1 represents a perfectly shaped element. The determinant of Jacobian relates the local stretching of the parametric space which is required to fit in onto the global coordinate space. Hypermesh evaluates the determinant of the Jacobian matrix at each of the element's integration point, also called as Gauss point, or at the element's corners, and report the ratio between the smallest and the largest. In the case of Jacobian evaluation of Gauss point, value of 0.7 and above are generally acceptable. So Jacobian in general terms can be defined as the deformation of element from actual shape can be reported as Jacobian. Then there are few last quality checks for 2D element, that is minimum angle tria and maximum angle tria. The ideal value for triangular element is 60 degree, but the acceptable range is from 20 degree to 120 degrees. Similarly, for the case of minimum angle and maximum angle chord, the ideal value is 90 degree and acceptable range is from 45 degree to 135 degree. Now let's move towards the next topic for the theory of FEM, that is when to use 3D element. 3D element should be used when all the three dimensions are comparable, that is x, y, z are comparable to each other. The element shapes available for 3D element in hypermesh are tetra, penta, hexa and pyramid. Additional data from the user required to simulate a 3D element is nothing because we define all the three parameters by creating the element itself. Element types are solid elements. These all are solid elements. They can be defined as tetra or penta or hexa elements, but they are all solid. The practical application where the tetra elements or say solid elements, that is either tetra or penta elements or hexa or pyramid elements are used, are gearbox, engine block, crankshaft, etc. Then we will discuss the types of 3D element. So we have different types of 3D element as tetra element. For tetra element we have two different class, that is linear tetra or parabolic tetra. Linear tetra has 4 nodes, so it generates an interpolation function using that 4 nodes. But the parabolic tetra element has a 10 nodes, so it generates an interpolation function using those 10 nodes. Similar the case for we have a penta element. In penta element we have 6 noded penta element, that is also known as linear penta element, or a parabolic penta element which has a 15 nodes for it. Then we have a hex or brick meshing. The brick elements or hex elements, there are also two categories for it, that is linear hexa containing 8 nodes and parabolic hexa containing 20 nodes. Same for the case for pyramids. We have pyramids for linear pyramids containing 5 nodes and parabolic pyramids for containing 13 nodes. Then we will discuss the degrees of freedom for solid elements. As in the case of 2D thin shell and 1D beam elements supports all the 6 degrees of freedom, but all the solid elements have only 3 translation degrees of freedom, no rotational degrees of freedom. That is, a 10 noded tetra element, that is a second order parabolic tetra element, has total of 10 into 3, that is 30 degrees of freedom. Why does a solid element have only 3 translations and no rotational degrees of freedom? So to answer that, we'll have a physical interpretation. Consider a piece of paper that is a 2D geometry or a long steel scale that we can consider as 1D geometry. It could be easily bent and twisted. As you can see on the images, we can easily twist and bend a steel scale or a paper. But now consider object like a duster or a paperweight. It could not be subjected to very high bending or torsional stiffness. Hence, solid elements have been formulated in Hyperworks with 3 translational degrees of freedom and no rotational degrees of freedom. So that's why a solid element have only 3 translational degrees of freedom, that is translation along X, Y and Z, but it doesn't support any rotational degrees of freedom. Then we will discuss the quality checks for tetra element. The rest of the quality checks for tetra element remain the same, but some of the quality checks added for the 3D tetra element, they are TET collapse. The ideal value for TET collapse is 1 and acceptable is greater than 0.1. Software calculates the TET collapse as h, that is height, into 1.4 divided by area of that particular face. So we can define TET collapse as the distance of node from the opposing face, that is height, divided by the area of the face multiplied by 1.24. So TET collapse defines the height of the tetra element. Then we also check for volumetric skew. If we create a sphere passing through the corner nodes of a tetra, then it should fit an ideal equilateral tetra in it. Then we find the volume of ideal and actual tetra element. So in this way we find the volumetric skew. Ideally the value should be 0, but acceptable range should be less than 0.7. So software calculates volumetric skew as volume ideal minus actual volume divided by ideal volume. Then for tetra element we also checks for stretch, that is its ideal value is 1 and acceptable should be greater than 0.2. The software calculate value of stretch as r, that is radius of largest possible sphere inside the given tetra element, multiplied by root of 24 divided by length, maximum length of that tetra element. Then we also check for distortion, that is its ideal value is 1 and acceptable value should be greater than 0.5. Software calculate the distortion function as modulus of j multiplied by volume of local coordinate system divided by volume of global coordinate system. Then we also consider Jacobian. Jacobian value is same, the definition is same as the 2D elements, but the ideal value is 1 for tetra elements and acceptable range is, it should be greater than 0.5 for tetra elements. So in simple terms, the Jacobian is a scale factor arising because of transformation of the coordinate systems. Elements are transformed from global coordinate systems to local coordinate system to reduce the solution time. So Jacobian is find out as the scale factor between local coordinate system and global coordinate system. Then we will discuss some quality checks for brick mesh. So in brick mesh we calculate warpage angle, the ideal value of warpage angle is 0. Acceptable should be less than 300. Warpage angle is calculated on face of each of the quadrilateral element of hex element. It is the angle between the planes that form by splitting the quad element. Then we also find the Jacobian for quad elements, that is the big brick elements, hexa elements. The ideal value is 1 and acceptable should be greater than 0.5. In simple language, the Jacobian is a scale factor arising because of transformation of coordinate systems. Elements are transformed from global to local coordinate system to reduce the solution time. Then we also find the distortion for brick element or hex element. Ideal value for distortion is 1 and acceptable is greater than 0.5. Software calculates the distortion function same as Tetra element. Now we consider some more types of qualities checks we consider for brick or hex meshing is stretch. The value of stretch for ideal is 1 and acceptable is greater than 0.2. Software calculate value of stretch as minimum edge length multiplied by root 3 divided by maximum diagonal length. Then we also check for aspect ratios, that is ideal value should be 1 and acceptable is less than 5. Aspect ratio for a for the hex or brick mesh can be calculated as maximum edge length divided by minimum edge length. Then we calculate skew angles for the brick meshing or hex meshing as its ideal value is 0 and acceptable should be less than 45 degree. Skew is a check on all the face of hex element, that is on each quadrilateral face of the hex element. For the skew definition, we can go, the definition will be same as 2D shell elements. Then for the minimum angle of the quad face or the range of the minimum and maximum angle of the quad face is same as 2D, that is it should be in the range of 45 degrees to 135 degree. And for penta elements, the tria face angle range is 20 degree to 120 degree. For a brick meshing, the percentage of pentas acceptable should be less than 5%. So in this way we have ended with this video tutorial related to the theory of 3D elements. So in this way we have ended with the theory of FEM by completing all these topics discussed in this tutorial.